to do the revision session?
It will be the same time next week.
Means Saturday.
Yeah.
Can you do it earlier? Because Sunday we have the exam. No, Saturday is very crunch.
Okay. We'll check and get back to you.
Okay.
All right, okay. Let's get started. I'll at least try to finish whatever is covered in the first video. A small run through of that. So yeah, we discussed why value function based methods, or rather the drawbacks of it from the DQN approach. We saw that it is guaranteed to converge when you use the tabular representation, but we saw how quickly that approach kind of falters when we have problems with huge state spaces and a large number of actions. And the first approach we took was to introduce the DQN, which is again a value-based approach. But because of certain trickeries we do there, like freezing the target network and using a replay buffer and so on, it doesn't really ascertain you to converge to some particular optimum. So it is quite prone to various problems, which is why we propose a new and simpler framework to solve stuff. So instead of having a value function and then inferring a policy out of it, we are proposing to directly search in the space of policies itself. And yeah, so why is it a simpler description? So sir uses this example of supermarket data. So where he talks about, is the thing annotated here? No. So where he talks about this example where if your stock is less than some predetermined limit, threshold, you then later order more stock. So that is the description of a policy. But if you were to make this into a value function based approach, then you have various parameters that actually are responsible to determine this threshold. So therefore, if you use a policy, it is much more simpler to describe what it is. And in fact, it was just an if condition, right? And also various other advantages like it converging better, even when you use a deep approach. And also it is robust to partial observability. All right. So yeah, so the way we do policy gradient is we first parameterize our policy using certain weights, theta, where these theta can either be action preferences. So in the case of softmax, it can be the mean and variance if you are to parameterize it using a normal distribution, or also it can be the weights of a neural network, which at the end actually predicts the probability of choosing each action as what a policy would do. So these are possible parameterizations for your policy itself. And the idea is to maximize this one, j theta, which is actually expectation of gt, where gt is the return, or more specifically, we'll see very soon, it's actually g naught, or rather, this is just v pi of s naught. Yeah. So we want to maximize this, and the way and from SGD, or mini batch gradient descent, the way we update is or mini batch gradient ascent, here it should be why is it gradient ascent? Because we are trying to maximize this metric here, and we are just going to do that. So how do we actually bring this to this setting? So to see that, the way we do it is, first instead of looking at it in the context of RL, we'll first look at it in the context of multi-arm bandits and see how it extends there. So in our multi-arm bandits, a small recap, we do not, or I can say RL is a series of multi-arm bandits. We are just looking at one part of it. So essentially just one state, and you have a bunch of actions you can take there, and then you get a reward and your episode terminates. So that's the multi-arm bandit. scenario. The rewards are from a distribution, so they need not be stationary. So you will have to sample a certain amount of times from each of the arm to really get an intuition or an idea of what distribution are your rewards coming from. And the goal is to pick the arm that has the highest expected reward. Cool. So we'll start off with policy gradient. This is the same slide as the last slide, except that, yeah, so we are writing this bit here. So this can be written as Q star A pi theta of A. Is this part clear? This is something I've referred to various times previously in the sessions, but why are we writing this? Is this part clear?
This Q star of A, that means I'm taking after drawing so many the optimal path of that action, right?
Mm-hmm. Do you know what Q star A is? What is Q star A? This I think comes from the first week, I think first or second week.
Yeah, we are first taking, it is the value function, but first taking the action A and then we are moving according to the policy plan.
No, dude. So we are in multi-arm bandits. So there is only one action to take, and your game is over, right? So yeah, we'll come to that later. So right now, to illustrate the policy gradient theorem, or perform policy gradient on a single stage, it's easier to explain it in this setting. So what is Q star A? Is Q star A dependent on theta?
No.
Why not? So what is Q star A then? So if you can answer that, then you can tell me why it is not dependent. So if you recall in multi-arm, yeah. Sorry, go ahead.
No, I may be.
All right. So the multi-arm bandit case. So suppose this is our machine, and we have arms. Say we have n arms, right? So we have arms, and and each of these are, say, part of some distribution. Okay, so each of these have a reward distribution, and we look at this expectation, right? And the idea is Q star of A. So Q star of A1, so say this is A1, A2 until AN. Q star of A1 is just the expectation of your reward, expectation of the reward R, provided you perform action is equal to A1. So this is just that. So this is Q star of A1 is literally the expected reward when you pick arm A1. So that comes from a distribution, and that distribution is Q star. Now, if we knew what Q star is, there is nothing to solve. We can just do argmax A, Q star of A, and then find the arm which gives us the highest expected reward. So which is what over here. So you can just find that and give it to me, but we do not have Q star, right? So that is the problem. Is that part clear so far?
Okay.
Is what Q star is clear? Okay, great. Now here, right, the expectation we are taking here, this expectation RT, or here actually T doesn't matter because it's just one step, is with respect to a policy pi, right? So this policy is some probability distribution across our n arms A1 to AN, okay? Now suppose, right, just for argument's sake, suppose my pi was this. Let me just write down my distribution pi. Let's see, how do I? Yeah, so say pi of A1 is equal to 1 and pi of A is equal to 0 for all A not equal to A1, right? So if this were my policy, what would E pi of R be?
If I have argued you one,
No, it won't be 1. It will actually be q star of 1,
yeah, make use of.
because this is precisely the definition of q star. But if pi is actually an arbitrary, or rather, if pi is not this way, but pi is stochastic, like it has some weights on all the actions. So here we use a definition of expectation itself and say pi is actually the summation of q star of A times pi of A. So theta is the parameterization. So the parameterization of pi and this. So is this part clear? So this is just the way you take expectations, because we are taking it with respect to pi. Since we are taking it with respect to pi, we have this. Here it can be
Okay.
put as theta, but yeah, it's clear so far, right?
Mhm.
And now we want to maximize this metric. So now the idea is, what is the gradient of this? What is the gradient? That's where we come here. So we take the gradient of this. What do we take the gradient of it with? With respect to theta, because that is what you can change. So we take the gradient with respect to theta. We saw q star A is a constant function. Q star A just tells us the expectation of the expected reward when you pick arm A, right? So there is nothing over there. So the gradient is only with respect, or the gradient, this triangle just directly comes to this pi theta of A, all right? And
Yeah.
and so we have this. Now to now to explain this next step, right? So the idea is we want to compute this gradient, right? And we are in this setting where we are sampling actions based on a policy pi. So this idea is actually called importance sampling. You can check that out. Uh, is when you want to estimate the mean of one distribution by sampling from another distribution. And that is where this name called likelihood ratio also comes. Let's not discuss it long, but the idea is this. So what we're doing here is we want to rewrite this. So we want to rewrite this as an expectation with respect to pi. So here we have this. We wrote E of RT is equal to pi theta. So this is actually pi, or rather theta, because it's parameterized by theta. We are able to do it this way. We again want to rewrite this as some sum, right? This is some sum here, but I want a pi theta A at the end, so that I can write this equivalently as E of this something, and call it a day. So that's what you want to do, right? So that is literally, so if I put pi, since I put theta, I'll just put theta here. So we want to write it this way, so that I can again rewrite it as an expectation, so that I can estimate it by sampling. Or what we do actually in the next slide is we put it as an incremental version, where we just do it for one sample and keep updating as you go along with sample. So an incremental version, if you will, right? So how do we write it with respect to this? We'll just multiply and divide by pi theta of A. That's literally what happens in this step. Clear so far?
No, can you just explain once more why you want to write again as an expectation of this thing?
Yeah. So here, this part clear? Why we are
Yeah,
writing
that's
it
not
this?
clear.
Yeah. So see this RT. Okay. Yeah. We'll come to this RT, right? Okay. Or rather, we have this 1 by n. Okay. Summation. Uh, R. Okay. Let's say. Uh, let's say I always pick action A. Okay. So I pick action A, right? Pick action A. I'm doing this experiment. I know I won't get the same R, right? So let me just call this R1. Uh, okay, Ri, sorry. I is equal to 1 to N, capital N, where Ri is sampled from whatever reward distribution is there for action A1. So which is this part, right? So I'm sampling it from this, right? This converges to q star of a. So I've just again said what q star of a is. This part is clear, right?
Mm.
Mm? In other words, we have that Ri, uh, or rather, Ri is uh, okay, or I can say this q star a is just the mean of this particular distribution Ra1. Yeah.
Yes.
And this is for this policy where the policy is pick action A or picks action A1, which is
Mm.
precisely what I wrote here. But if it were not that particular policy, if you had a policy where the weights are sort of distributed among many actions, then you bring in this pi theta of A here. So this is how an expectation itself is calculated. So you are taking an expectation with respect to theta of some quantity of interest. Here it happens to be a weighted sum of q star a. That is what we are doing here. Similarly, over here, we want to write, see, we already have j theta as an expectation, right? Now, what I want to do is write grad of j theta also as an expectation. Now, why do I have this as an expectation? Because I have this pi theta term at the end, which is what I've written here. Let me actually just write this again. We have expectation. So say I sample from G, okay? Expectation, I'm sampling from G of f of x, right? This is the formula I want you to take, like, seriously understand, because I think I've been mentioning this across all my live sessions. So this is exactly, so in the discrete case, this is exactly just f of x g of x, or in the continuous case, an integral. I saw this was actually also a valid symbol. So this is our thing, right? So we, if I want to write it expectation as with expectation over theta of rt, I need this pi theta of a at the end. Now I am seeking to do the same thing with my gradient vector grad j theta, right? So I have on the right hand side, I have q star of a, grad pi theta, but I do not have this pi theta in this expression, at least not yet. So I'm bringing it manually myself. So I'm multiplying and dividing by pi theta of a so that I have this at the end, right? So therefore, this, according to this expression, this part is my g and this part is my f. So I can therefore just write this as expectation of g given f. So that is what we are seeking to do here. So we want to rewrite this again as an expectation with respect to theta or with respect to pi theta, which is why we are doing this multiply divide business. Once you do that, you this is one instance, or rather this is one instance of the gradient that is actually sampled from a gradient distribution, if you will. And if you want to estimate the gradient with n samples, you take n of these samples and then take the average, right? So yeah, actually sir has written the extra line that I just want to write. See, so he's written, so this part, e pi theta q star of a. So it's only this part, whatever I've highlighted in this box comes into this pi theta actually becomes your expectation. So it's with respect to pi theta of a, or in other words, you keep sampling action a from pi theta of a and you get this. So a empirical way to estimate this expectation over pi theta is what? Number one, sample a from pi theta, and number two, calculate q star of a pi theta of a over pi theta of a. So this is your one sample estimate. So this is actually one sample estimate of what? Of grad j theta. So this is what we have. If you do this like n times, if you do it large enough times and take an average of it, you will get a much better estimate of your j theta. Right?
Mm.
Okay. There's also not q star over a over here because we don't have access to q star a. So instead, we saw that Ri equivalently was also it also converges to q star of a. So whatever I wrote here, that q star of a is equivalent if you take this, if you consider this I is equal to 1 to n Ri. So Ri is a sample of q star of a, and you also have Ri. So therefore, Ri times grad pi theta of a divided by pi theta of a is one sample. Uh, once is a sample of your gradient of j theta. Does that make sense?
Yes.
Great. Okay.
And why you are calling this as an important sampling?
Important sampling because you are, see, the thing is I can yeah, I don't, yeah, let me not, yeah, if you can look it up separately. I don't think the idea is you want we want to use, so here we are sampling from policy pi a, right? But here you see that the reward is also sampled from these distributions, right? So Ri is sampled from this distribution,
Mhm.
right? But we do not at least explicitly have access to this particular distribution. We are actually using the policy pi to later sample from this. Whereas this expectation, right, here it has q star of a, which implicitly is calling the multi-arm distributions over here. So if you were to actually do this properly, right, this is not required. You have to do this for summation. Okay, you can't do that, but rather you'll have to do uh, 1 by n summation capital N I is equal to 1 to n Ri with respect to theta, provided policy or rather provided you use theta, and then you multiply it by grad pi theta of a. So here the distribution you're actually sampling from is 1 pi theta, but 2 also these other multi-arm distributions. So but you do not have access to those things. So instead you're saying, I'll only write it with respect to pi theta, right? And then I'll calculate the estimate as the following. So yeah, we are changing the distribution that we are sampling from to obtain our answer. That's why it's called importance sampling. Uh, and yeah, so yeah, if you're interested in that, do look it up more. It's also covered in the statistical computing course. But that is the idea here.
Achha. Okay.
That's fine, right? Cool. And this was the last slide for that lecture. We saw that this is our we take n samples to estimate the gradient. But if you just choose to do SGD using one sample, you can write this as an incremental version. Just take one sample of it, perform the update, you'll get a new theta, and you again take a sample, perform the update, you again get a new theta, and so on. So that is the incremental reinforced version. Whatever we have here, alpha is just the step size, RT is your Ri, but RT in the sense is RT is the first sample, like, so you have theta t, uh, uh, and then you sample an action from this, or rather, so you have theta t, so sample from pi theta t, obtain some a, right? And then sample, the third step would be to sample RT from, what notation did I use here? RA, right? Yeah, from RA. So which is the reward distribution associated with action A, whichever one you sampled. So that would be over here. So it's just one sample. So you take that, calculate this, you will get your gradient, and just perform the update. Also, a way to simplify this is you just have to recall that this thing, this particular thing, is just the derivative of the ln of your policy. Did not recall, derivative of ln of f of x by dx is equal to 1 by f of x times f dash of x. So that's where this comes from. This is the multivariate uh, generalization of that. Is this part clear? Finally, we also include a baseline. The idea is your rewards are in some arbitrary scale. So sometimes you can just have rewards where you get 10 and rewards where you get 1,000. But where your reward with 10 is perhaps a worse reward, and you want to indicate that you do not want to consider all your rewards to be equally good, right? So therefore we bring this idea of a baseline where your rewards become comparable. This is very similar to the idea in dueling networks where we talk about advantage, and we do that by if you recall the neural network implementation of dueling networks, you have either a minus max of all your value predictions, or minus, or rather you mean center it, so minus the mean of all your action predictions. Similarly here, this baseline is generally the average of your RTs, right? RT, where this is from 1 to n, so which actually makes your rewards differentiable. So if you have a negative, so in other words, if you have a negative reward, this actually, or in the sense, if you have a reward that you could consider to be on the lower end of the spectrum, so like this is what I mean. So this is 0 and these are like negative ones, but you have a reward spectrum like this, right? So and if you get a reward over here, then this is definitely a bad kind of reward. But in this kind of framework, you see this at least this part is positive, RT is positive. But when we do the RT minus BT part, it actually makes sure, so BT would be here, hopefully, since it's an empirical estimate, it should be close over there. RT minus BT actually ensures is actually negative, so you'll actually get a negative quantity over here, right? So you'll actually get this part negative to actually be this constant, so it becomes a negative sign, so which actually indicates that the direction is the other way around. So yeah, that we have. You also need to ensure that this BT, the only thing you need to ensure is that this BT is not a function of action of A or AT. If you ensure that, this thing holds. In the RL setting, this is generally a function of your state. So BT is generally just set to be your, or not BT, let's just say B, the baseline, is generally set to be the value of ST. The value function of ST, which is just expectation of GT given ST. S is equal to ST, which you will see very soon. It's called the actor critic method. But in reinforce in the multi-amp bandit case, since there's just one state, you can just think of this as the expectation from that. So yeah. Right. Okay. So that was the end of the stuff covered in the first video, at least. Any doubts so far? Any place you think is lagging? No, right? Okay, great. Are there any other doubts from this week from anyone? Any conceptual doubts? It can be from the other two videos. So I see Achit has also joined, right? Are there any parts in the other lectures that you're confused about that I can go through and clear up? Okay, all right then. Great. If there are no doubts, can maybe close this session till here.
No, you will go through the other two part.
You want me to?
Actually, I have not seen the video from
Exactly, yeah.
reinforce on
So
board.
that is why I'm not going through the other parts, because it doesn't make sense then. Like,
Okay.
because as I said before as well, the professor does a better job at going through these slides than me. If there are any parts where you feel doubtful because the professor may have not covered that in depth, that is where I can come in and assist you and tell you, okay, this is what is done here. So if you guys
then
see
I have
the
to
sessions
go through
beforehand and
first.
come, that is when these live sessions actually become useful. So which is why I cover the first set of slides, because you said you did, which is why I went through and maybe covered doubts along the way. If you guys have seen the other parts of the slides, and if there are any specific parts of it that you feel you have doubts in and you want me to go through, I am happy to do that now.
No, I haven't seen that, so I cannot say that.
Okay, all right. Yeah, so if there are no further doubts, we can close the session here.